So good afternoon, everybody, and welcome to our weekly seminar. Today, we are excited to have a guest presentation from Dr. Mandela Patrick, who recently completed his PhD at University of Oxford. And so we are delighted to have him present on his thesis, and anything else he wants to present on. Anything he has to present will be, I'm sure, of interest to us. I will let Mandela talk more about his background, and so yeah, Mandela, take it from there. Let me make you co-host, so you should be able to share now.
Sounds good. Thanks for having me here. This is a bit about me. Name is Mandela Patrick, from San Fernando, Trinidad and Tobago. Did my high schooling at Napima College. Did pure math, applied math, physics, information technology at A-levels. Was the top student in the Caribbean in math and information technology. Then did my undergrad at Harvard University, where I spent 4 years doing computer science. Got interested in machine learning AI there, particularly after a summer interning at Instagram on their machine learning team. Won the Rhodes Scholarship to pursue my postgrad studies at the University of Oxford, where I did my research in computer vision in the VGG group, which is popular because of the famous convolutional neural network. Did my PhD there on multimodal video understanding. Spent quite a bit, or pretty much all of my PhD at Facebook AI in London and New York. And yeah, recently graduated maybe a couple of weeks ago, and have started as a machine learning researcher / scientist at this startup called Pinata Farms based in LA. And my presentation today is going to be sort of like a few words from my PhD thesis, which was on how do we learn and interpret representations from unlabeled multimodal data. And with that, I will share my screen. Can everyone see?
Yeah, we can see.
Sweet. Is there any background noise by chance?
No.
No background noise.
No.
Perfect. So yeah. So to give a little bit overview, you all are probably familiar with what a representation is, but I think this gives a pretty sort of semantic understanding of what happens with the representation. And so essentially, you could think of a representation of mapping stuff in what we call input space, and to a set of numbers in vector space. And the sort of high level idea is that we want semantic similarity in the input space to be mapped in terms of vector similarity in representation of vector space. And so what that looks like is that if you have two images of, say, someone riding a bicycle, you would visually, they're semantically similar bike person. You would, and then how you want to represent that is hopefully that when you map this to a set of vectors, they're quite similar in vector space. And on a high level, a good representation is what we call invariant nuisance factors, meaning that features that are unimportant for semantics, you want the representation to ignore, and features that are important of sense, we want the representation to be sensitive to. And so in this case, common nuisance transformations include stuff like color jittering, like the semantic information doesn't change if you add different sort of color information, or usually if you rotate an image, the semantic aspect of the image doesn't change. But for example, if you change if you crop out an image and replace it with, say for example, like a dog, you would expect the semantics to now be different. And so what a representation looks like is that you want to map those stuff which are semantically similar nearby in embedding space, but those which are far apart to be different. And so normally what that looks like is that you usually have human annotated labels to learn this representation. And so, for example, the popular ImageNet dataset, it was labeled over like, I don't know, 5-10 years or something along those lines. And basically we assign the same label to images which are semantically similar, and we assign different labels to semantically different images. And so the ImageNet dataset is like 1,000 classes. So we have X number of images in each of the classes. And by training a neural network to predict the label from given an image, it's able to learn a good representation of the data. The problem is that labels are quite expensive. They're quite expensive to obtain. So as I said, it took a while to get labels from images, to get the ImageNet dataset labeled. And so, but if you think about the amount of unlabeled data that is uploaded to the internet every day, I think from my experience at Instagram, it's over like 9 billion pieces of content uploaded per day. You would hopefully want your model to sort of be able to learn from all of this unlabeled data, but you cannot label 9 billion images per day. It's pretty much impractical. And so a lot of the holy grail right now is how can we learn representations without any sort of human annotated labels. And the prior we use is that we could essentially approximate on a high level what these representations are hopefully learning. You want it to be invariant to, as I said, nuisance transformation, and then sensitive to something like image identity. And what that looks like in terms of a learning objective is a contrastive loss. And so essentially you sample, say, n images from your data set, and then you apply 2 pairs of transformations to that input. So in this case, X1, we apply, say, color jitter, random cropping, random flips, etc. And essentially we get 2 pairs of transformation per data point. And then essentially, because these sort of what we call augmentations don't really alter the meaning of what's semantic in the image, we could sort of make an assumption that these pairs are sort of semantically related and should be pulled together, while a randomly selected transformation from other images on average is usually not that semantically similar, and you could sort of push that apart. Some examples, as I said, of these semantic specific image transformations include stuff like color jittering, random cropping, rotations, etc. But what about videos? So videos that was sort of the focus of my PhD, and for me it's a lot more interesting because videos have multiple modalities. And so when you think about, they have audio, then you could have a lot of these YouTube videos have, for example, titles or English captions, also captions in multiple languages, and then you could extract other sort of semantic modalities such as optical flow, which gives some prior on the sort of low-level motion information happening across frames. And the idea here is just like how with images, we could apply certain sort of augmentations to the image, and we know that the core semantic information is still intact. Similarly, like usually the visual stream or the RGB stream, as well as the audio stream, usually sort of correlate to some sort of latent semantic meaning. So in this case, like, let's say, like, for example, like a much easier example is say like playing a guitar. Like the visual stream is communicating that someone is strumming some strings, while the oral part is also communicating that like this is a guitar and someone's playing a guitar because it sounds like a guitar. And so what that looks like is sort of contrasting modalities. And this was popularized by work in my lab and at MIT. And some of these works are listed here. And so, for example, if I show this video, this is someone playing an electric guitar and someone playing a drum. If I now play the songs, not sure if you could hear it, but hopefully you can. Even though that song matches to the guitar, but even without like seeing the guitar, you know it matches with the guitar. While like this is a drum song, which matches with the visual of someone playing a drum. And so I think the sort of motivating idea of this example is that modalities carry a lot of, like modalities occurring at the same time carry a lot of semantic information. And essentially it's a good prior of essentially correlation or grouping stuff that are related. So this was sort of the motivation for this work, which was a recent ICCB paper on compositions of transformations for self-supervised learning, work I did at Oxford, as well as some folks at Facebook. And just to rehash, the idea, as I said, is essentially we have it's this sort of learning where we don't require labels. It's called self-supervised learning. And it usually finds some sort of pretext task where you essentially artificially construct labels from the data itself. For example, one might be predicting the color from a grayscale image, or predicting the degree of rotation given some input image in the image domain, while on the video domain, stuff around sort of like predicting the order of frames, or predicting in the sort of like multimodal context, which is a lot of my research is predicting, say, whether a video and audio pair are sort of at the same time or from a different video at different times. And so to sort of develop that as a sort of learning objective, it sort of grouping pairs of inputs you have some prior to be similar, and pushing apart pairs of inputs which you have some prior that on average is not similar, is using this approach called noise contrastive learning. And the idea here is that essentially you want your representation F to essentially be approximately similar for, as I said, an image, and say, for example, an augmented version of that image. In this case, it's grayscale, but you want the representation to be different for, say, some different semantic class. For example, let's say a dog in this case. And this approach was popularized by works such as Moko, Sinclair, and CMC, which, for those who are familiar, sort of led to this seismic shift in how we think about learning these representations without labels. For example, here again, this is sort of, as I said, predicting this pretext task is given some image. Let's predict what is the degree of the rotation. And the idea here again is that if the model is able to sort of solve this task, it would have hopefully learned a meaningful representation of the data, because most images stay upright, for example. And sort of a lot of the core crux of this stuff is essentially learning is essentially encoding what you want your representation to be invariant or distinctive to. In this case, let's say the direction of time. Do you want your representation to be invariant, meaning that you want it to map both the forward and backward and reverse clips in the same point in space, or do you want to map them further apart? And so with videos, because of its temporal dimension, and because a lot of this, and because of the multimodality, we wanted to explore what sort of signals do you want the representation to encode invariance, and which ones do you want to encode distinctiveness. And this was the motivation for our GDT work, where essentially we can express everything as a set of transformations, and then systematically explore whether the representation should be invariant or distinctive to these different sort of transformations. The ones we explored, so for example, let's say you have a collection of videos. First, we sample, say, N videos from the data set in our batch. Then we sample 2 different times in those videos. So time 1, tau 1, tau 2. And then we extract both the visual or the RGB stream and then the oral component. And then that gives us, say, some final transformed sample, and then we map usually say video and audio from the same time and the same video together in space, and then we sort of push apart the audio and video from different videos at different times. And this just goes through a specific instantiation of this. And so the ones we explored, as I said, is sort of sample distinctiveness. So we know that, for example, say two randomly sampled videos are usually you do not have the same information. But we won't show, for example, whether we want the representation to be reversal to time. Because if you think, for example, if you think about, say, let's say, like a train moving in, say, either forward or backward direction, like in terms of the high level semantics of a train moving, forward or backward doesn't really matter. Like even if you sit on a train, you usually like sit in a backward or forward direction, like it doesn't really matter. But say, for example, for stuff like, say, an action such as like driving or reversing, the direction of time actually matters. And then you're interested in sort of like whether shifts in time, and so whether semantics, it changes slowly across a video or it changes quickly. We sort of explored different combinations of this stuff, and we found that different combinations are optimal. And then at that point in time, how essentially once you've learned your representation using these sort of pre-training objectives, you want to essentially measure how good the representation is. And so typical tasks include stuff like action retrieval. And so essentially you sample multiple clips from a video, and then you want to find what is the nearest neighbor in, say, the validation set. And if the nearest neighbor in the validation set belongs to the same class, that means you can retrieve quite well. And so so basically on some new data set that you haven't even seen, can you, because you've learned some good representation of the data, can you essentially see what two stuff are similar? And so what we saw is that, yeah, we got like a 2x improvement on retrieval on two very popular data sets, UCF 101 and HMDB 51. Because we pre-trained on, say, like 60-something million videos on Instagram. And so yeah, basically the high level idea is that essentially the paradigm has shifted from pre-training on large-scale supervised or labeled data sets to pre-training on even more large-scale unlabeled data sets, but constructing these sort of pretext objectives that basically generate these free labels from the data itself. And so to give you some context, like the popular like video pre-training data set is Kinetics. It's of size maybe 200,000 videos. And each of the 200,000 videos are labeled with one of 400 classes. And so 400 classes is a very limited distribution of the visual. Like there's more than 400 actions that someone could take. And so because you have to restrict yourself to these, like you have to label these data sets and construct this label taxonomy, it's very limiting to sort of learn a very like long tail distribution of visual concepts. And with a lot of these self-supervised learning, we no longer are bottlenecked by labels. And so we trained our model on 65 million videos on Instagram. And we were one of the first works to show that if you pre-train on millions and millions of videos, you can learn a very good or just as good representation of the data as relying on labeled data. So I'll stop there for now and take any questions.
Yeah, thanks for that, Mandela. Interesting stuff. One thing that will come up though is the energy requirements to do this kind of stuff, right? I mean,
yes. So that's I think the sort of nice part about one, where the field is going, and a lot of this sort of methodology of learning, of representation learning, is that a lot of these big companies do the hard work for you of training these very large scale models on very large scale data to learn a very good representation. And then say you, for example, who have some specific task, let's say it's like medical imaging, or whether it is, say, forest, something regards to like climate change. Like now you could just take that very good representation and then fine tune it on your much smaller label data set. And it works significantly better than if you were to train your model from scratch on that data set. And so, for example, this work is open sourced, and the model we trained on Instagram is publicly available. And yeah, for example, let's say you have some new video data set focused on, say, like sports videos. If you were to train, say, a common CNN, like your, let's say like a ResNet 50 CNN architecture on this, say, like 5,000 video sports data set with, like, say, 50 classes. If you train that from scratch, you'd probably get 15-20%. With if on the other hand you initialize, say, your ResNet 50 with, say, my checkpoint that was trained on Instagram 65 million, you could now train on this sports data set and you get maybe like a 3x. So like maybe from like 20% you go to like 60-70% in terms of performance improvement.
okay, so you're gonna basically you're doing the heavy duty work and providing a kind of startup kit to do the rest of it. Okay.
And so that's what you've seen, for example, like this is what OpenAI has done with like GPT-3 and the clip model that was released, is that these things are trained on millions of images, but like out of the box, you just deploy these models or you fine tune it on some small label data set. You get significant boosts in performance that you just cannot get training these models from scratch, or training any model from scratch on these small scale data sets.
So
yeah.
By training on these big data sets, you're basically extracting some information, a smaller set of information. Have you been able to look at that and see what it's extracting from this bigger data set?
So yeah, so that's sort of the next part of my thesis, which is interpreting representations. But yeah, so basically, like, as I said, like if you think about this, like a representation is just a set of numbers in RD space, and you would hope that there is some sort of semantic or vector similarity in that space. And so one, it just empirically just works. Like empirically, it just works. And then I have some interesting work that I'll share on how we could sort of maybe get an understanding of what kind of stuff these models are learning.
Okay, thanks. Yeah, anybody else have questions?
Yeah, hi. I have a couple questions. They're all interesting work there. So tell me something. So just so I understand. So you're using the additional components of a video as hints as to what the representations should be, and then learning from that. So it's not just the still frames themselves, right?
Exactly. So the idea is that so what, for example, so there has been recent progress on this, but at least a lot of like my initial research on this, like if you take a lot of these like image-based pretext tasks, so for example, let's say predict the rotation of an image. Now this has moved to like noise contrastive learning, where like two pairs of similar, push two similar pairs together, push apart the similar pairs, and you directly port it to the video. What happens is that so the problem with a lot of these like self-supervised learning is that a lot of these models like cheat. And so they essentially look for low-level information that can help them solve the task. And it's much easier for the model to cheat on video data because they could leverage the temporal smoothness of video. And so what we found is that by instead training the model to predict different modalities or to correlate modalities, it has, because it now has to think on a much more high level of what makes these stuff correlated, or what makes these stuff similar. It now has to ideally extract some sort of more semantic representation of the data. And so with a lot of these, like what we found is that these multimodal approaches to learning representations on video perform significantly better for learning video representations. That some recent papers have been able to show performance without having to rely on multiple modalities, but it requires either like a lot more training in terms of epochs. But there has been some recent works which have been able to get it with less epochs. So I think it's a lot of this stuff people are improving and figuring out different tips and tricks to get these models to cheat less. But yeah, just generally the idea is that like figure out some task that forces the model to learn some meaningful representation of the data, train that on large scale unlabeled data, and then use that representation on smaller labeled data sets that you care about. And you would get massive improvement in terms of performance is the paradigm.
All right, cool. So one question I was leading up to was so like how much of these modalities are necessary? Because I'm thinking like if you want to apply it to, let me just say, audio alone or image alone, where there's no temporal, no other types of additional stuff, how does it compare? Like would the strategy default to what we currently do with normal neural nets or something, or would it still have an edge? Or it will figure out it will sort of suss out a new modality, even though it's a still image. Like it could probably figure out RGB on its own. How would that work?
So it depends on the pretext, depending on like what task or learning objective you want the model to do. What we found that works best on most cases is the contrastive learning framework, where essentially you have some representation of the audio. Let's say you represent the audio as a spectrogram. You pass that through a CNN, you get some late layer representation. You pass a sequence of frames through a 3D CNN, you get some late layer representation. You map those 2 points together because they're from the same video. Then you randomly sample from your batch another video, you extract its visual and audio component, and then you sort of push apart those because you sort of assume that they're dissimilar because they're from a different, like, so if you on a high level, for example, like this video X1, you could assume that the visual and audio component at the same time are semantically similar in some way. While, for example, if you look at another video X2, the visual and audio component on average is dissimilar. And so you map the pairs of input from the same video at the same time and the visual and audio modality together, and then you push apart it from other videos. Is the high level task. You could do other tasks that involves multiple modalities. Let's say you predict video from, given a video representation, you try to directly regress the audio representation. But the problem with that is that it doesn't, you need to have negatives in some way or some priors on what's dissimilar for the representation to actually learn anything. Otherwise it just collapses.
But those transformations that you're using to map them into the final space, those are functions that you define, or it sort of learns that on its own? So like
So,
the T1,
yeah.
T2 like this.
So T1 is all of these transformations that was applied before. So like, well, actually, well, that's not fully correct. So T1 on average is stuff like stuff we know that we want the representation to be invariant to. And so we know, for example, that color jittering on average applied to this an image should keep the same image, should keep the same semantics.
Right.
And so we have some priors already on what transformations are what we call invariant or invariant transformations that would keep the semantics intact. While we have some prior, like the best prior we have that we want our transformation to be distinctive to is some randomly sampled image from the batch, because on average that would be a different semantic image.
Right. So it's just a stand-in for some generalized perturbation of the information that you would select as important based on the task.
Yeah, exactly. So there is some task specific knowledge you would have to have. We know for images and videos what kind of transformations are usually important or that would encode invariants, and then we know on average that a randomly sampled image from the batch is distinctive or shouldn't be semantically related. So I think there has been some research on can you like learn the transformation that is optimal for a task. All this stuff, it just doesn't work as well, and just hand engineering and trying a bunch of stuff usually gets you over the line.
Okay. All right, yeah, because I'll be really interested to see how this would apply to audio or scenarios where you don't have so much modalities. Because it's an interesting approach, right? Because there is hidden information in other aspects of the data. So in situations where there are low modalities, can modalities be generated automatically? Would be interesting. So that was I wanted to know, like, if there was a dramatic scale back in terms of the number of modalities that would yield benefit. Like if you had 5 to choose from and 3 was like you didn't get much benefit from 3 to 5, then you could say, okay, we could just stick with 3.
Yeah, so that's the thing. We didn't explore more than 2, at least in our work. So we just focus on video and audio usually.
Right. Okay.
That was stuff we wanted to try. So people have used video, audio, and text as well, and video, audio, text works better than video, audio. So I'm pretty sure for like videos, video, audio, text is the optimal combination, and maybe optical flow as well. So the thing is, we would love to explore like trying to add as much modalities as possible and seeing whether we improve the representation. But video, audio is a good start to video, and then text as well is also a good modality to play with.
Okay. But how does this compare to like one-shot algorithms and stuff in terms of classifications?
So retrieval is basically a one-shot task, or actually it's a zero-shot task. And so essentially you you represent some video and then you want to find what's the nearest video in representation space. And so after we pre-train this stuff on Instagram, it is actually very good. Like 57.4 recall at 1 is pretty insane. And that's basically zero shot. You've never seen, you take a representation pre-trained on Instagram, you apply it to some new data set, in this case HMDB51, and then you task the model with basically finding the nearest video, and on 57.4% of the times it finds the top video is in the same class. And so
why I asked that, because I was thinking this would be a real interesting application for face recognition. Because sometimes like if I take a haircut or a shave or something, this can recognize the face and I'll be like, what's up with that?
So with a lot of these images stuff, augmentation or transformations is like the biggest factor to get this stuff to work really well, because it just inflates the data and just give the model a lot more stuff to see the distribution. And so a lot in both self-supervised and supervised learning, I think one of the biggest factors for performance is just the augmentation and transformations you apply.
Okay,
Hi.
okay. All right, good stuff. Thanks.
Hi.
Hi.
I would like some information about data augmentation or image augmentation. Do you know, like, where I could go and get some more information about that?
My paper is a pretty good place to start. So yeah, if you just look up my Google Scholar, you'd see a few of my papers. The one on multimodal self-supervision is a pretty good one to start. For videos, for images, simpler. What's the full name of the paper? Let me quickly get it. Yeah, this paper is. So, how do you send stuff? Yeah. So yeah, basically this paper is probably the state of the art for images in terms of augmentation, etc.
Thank you.
How can I remove this? So I'll probably end off with another work which I think is pretty interesting. It's also multimodal, and in this case, we want to essentially learn, as sort of Professor Wilson alluded to, is that to get a sense of what these stuff are learning. And so in this case, the task we want to do is that given some unlabeled data set, can we automatically group them, basically? So essentially learning labels for unlabeled video data. And sort of the same story again, manual annotations are expensive, data is cheap, annotations are not. And here are some works which try to essentially to learn labels in a sort of unsupervised manner. So for example, here, like we can, even if we do not know what to call this, we can visually group these 4 images on top together, say like a tree, and at the bottom, let's say mountains. And as humans, we sort of have some, as I said, some semantic understanding or could visually group stuff. And so can we sort of train a model to do something similar? And it's the same story as before. Can we leverage multiple modalities to help us do that? And so if you hear that song, you could hear that it's a saw. Similarly here. And then here, you could hear it's a piano. And so modalities, again, as I said, they encode some data and semantic concept and could sort of help us to group or label visual data. And so normally when we have labels, we train a model probability of y given x. So given some input image x, we want to predict the probability of some ground truth label YGT, and it learns some distribution, and then we train it with softmax plus cross entropy training. But what if we do not have labels? We need to come up with some sort of like pseudo labels. And what that looks like is you want to optimize both the representation phi, and then you also want to optimize the labels as well. But if you try to do them jointly, leads to non-trivial, it leads to a trivial solution. And because the trivial solution is just to set all the labels to the same point, is the easiest way to satisfy this function. And so what this function represents is that you want to, for all the images in your data set from I equal 1 to n, you want to maximize the log likelihood of the ground truth class y. So what we did is that we enforce some constraint where we essentially force the labels to be used an equal number of times. And so we enforce some equipartitioning constraint. And that is posed, and that can be solved efficiently using sort of an optimal transport objective. So let's say we have some sort of set of images 1 to n. We want to assign some semantic label to each image. We essentially, given our current model parameters, we find the optimal permutation of the labels that maximize this cost objective. And then essentially over time, this should decrease. And in subsequent works, we looked at changing this equipartitioning constraint to sort of other sort of distributions like Gaussian and the Sift distribution. And so what that looks like in terms of training is a combination of essentially normal cross entropy training, where we just, given our set of labels at the set of labels right now, we do cross entropy training, and then we optimize the labels, and then we alternate between these two steps, between labeling the data set and then training the model. And for multimodal data, what that looks like is essentially we have audio and video again, labels 1 and well, audio and video, and other works, for example, might essentially try to label each modality independently. And so what happens there is that you don't share any information. And then you have different sets of clusters for different modalities. Another way to cluster multimodal data is to concat the audio and visual representation, and then perform labeling on top of that joint representation. But then you have this sort of maybe mismatch in terms of stronger modality, etc. And so what we propose to do is essentially view, as I said, video and audio as an augmentation or having some sort of similar semantic content. And we want the model to predict the same cluster or same label, irrespective of which modality we choose. And so what that looks like is that, as I said, essentially we take the expectation over both audio and visual, and we predict the sort of the same label. And what we found, at least on most data sets, is that, again, here, if you just do the clustering, unsupervised clustering in the visual modality, it doesn't work that well. But once you add multimodal information, it improves significantly. And then another way we could do this essentially is pre-train a representation and then cluster in a post-hoc manner. So either you train a representation using, say, supervised pre-training, or you do unsupervised pre-training using some of these other ideas. And then you do k-means clustering on top of the representation to learn some pseudo labels. And what we found is that our approach of simultaneously clustering and representing data works better in terms of learning semantic labels of the data set. And then to show you some examples, so this data set, VGG Sound, which is out of my lab, what we did here is that we could sort by entropy, or sort by entropy. And let's say this, so the model doesn't know the name of the label, but it could group it in terms of what it thinks are semantically similar. And so let's say cluster 258 to the model. If we look at the videos, it's able to find without any sort of human supervision, or most of the half videos. If I pick another class, let's say 28, it finds a bunch of church bell ringing videos automatically. Here, it's a bunch of ping pong videos. Here, skiing videos. And I think this was probably one of the coolest ones I think out of my PhD is that, yeah, we could essentially learn to automatically label or group videos in a data set without any sort of human supervision, using some of these multimodal ideas. And yeah, it works in practice quite well. Yeah, as you can see, and I can share the link for people to play around with. Yeah, but that's pretty much it. Happy to take questions.
Yeah, that's amazing. It was able to do this unsupervised. I have a more general type of question, Mandela. So, you know, if we look at Trinidad, where we have a small population, our data sets tend to be small. We can't really do much in many cases. And so if we use any platform from abroad that has been trained on much bigger data sets, but not, you know, the usual bias kind of problem, would this kind of help resolve some of those problems we would face, that, you know, we have a small population, we don't have the data, but we can't really use anything trained on the outside?
So yeah, so I think, if you had a task in mind, I could probably give a bit more specifics. But yeah, I think what we're seeing is that this is at least the immediate to near future of how AI is moving, is that large scale unsupervised pre-training plus downstream fine-tuning on some smaller task-specific data set just works really well. And so we're seeing similar stuff in terms of speech and natural language, where you pre-train this stuff on millions of examples, and then given some new language that you've never seen before, the model could generalize very well with very limited data, for example.
Okay, well, yeah, and I'm sure you're familiar with the usual facial recognition problem with black and brown faces, right? Not working well. So you think this would be able to address some of that type of issue, to be more specific?
So yeah, so I think it's a few solutions. Like, I think large scale pre-training, I think the right augmentations, and then we're seeing a lot of use of, say, synthetic data to essentially sort of clean up a lot of these distribution challenges. I think facial recognition is more or less a solved problem. I just think that, like, they are just, like, a lot of these problems we're seeing is more a factor of people not doing the right due diligence on model evaluation and model testing. But in terms of, from what I've seen, like my startup does a lot of like face recognition technology. It works well on pretty much every distribution of faces. I just think it's a matter of, can you get enough of the training data, and it's just being conscious of a lot of these more subtle biases that you might really focus on.
Okay, nice, thanks. Any more questions?
Yeah, just one general thing. Can this be used for compression? I'm not sure how big the final model is, but I think if it can find these clusters really good, then should be able to
Yeah.
get something better than entropy for compression, right?
So yeah, so this is something we were like thinking of, but by definition, a representation is a form of compression. So if you think about an image or video is, say, some input in very high dimensional space, like on average, let's say 224 by 224 by 3 by 30. That is very high dimensional. Representation is on average 256 to 500. And then if you use stuff like mixed precision training, where you go to like float 16, it gets even more compressed. And so that's been sort of the shift we're seeing just generally, is that if you're able to learn a very good representation of data, you could pretty much do a lot of stuff. So in this case, it's a compressed representation of some input. Then you could do stuff like recommendations, nearest neighbor search. You could fine tune that on some downstream task. And so I think what's exciting is that this whole paradigm of unsupervised pre-training or large-scale pre-training is essentially, once we've solved that for the most part, I think the democratization of AI is pretty much at our fingertips. Yeah.
But of course, it still requires quite a bit of resources to do stuff like this. So still only the big tech companies will be able to do this stuff, right?
So, but I think that's the cool part, is that they do all of the hard work in some sense in terms of pre-training these labs, but then we get to use that on the tasks that we care about. Okay. And so that's what I mean about like democratizing AI, is that like even stuff, for example, says understanding languages. In the example I brought them into the low resource language understanding, where, for example, if you go to say places in Africa or Asia where there isn't much label data in a lot of these languages, with this large scale pre-training, what we're seeing is that some researcher in, say, Africa or Asia with some very small label data set can now take these large scale pre-trained models and train a good speech recognition model in their domain languages that they just couldn't do so before. And so yeah, I think it's an exciting future for democratization of AI, because I think that a lot of these big companies, it's in their best interest to train these models and then open source it. And then we get to sort of do a lot of these domain specific and interesting tasks using these representations.
Okay, nice, cool. Yeah, so you should have a lot of startups hopefully using this to benefit smaller countries.
Yeah, so we're seeing us already, like, so if you think about GPT-3, so GPT-3 is a very similar sort of paradigm. It was trained on, I think, terabytes. I don't even know at this, but terabytes of data. And then in a pretty much zero-shot manner, it's being used for a bunch of different stuff, for many different applications. And it's opening up so many startup opportunities that we just haven't seen before, because you have basically a generalized language processor at your fingertips. And so creatively using the technology is sort of now the interesting part, rather than figuring out a lot of these more hard tech challenges that these companies are solving for us.
Nice.